In this presentation, I am going to introduce the next unit that we're going to study, which is called stoichiometry. Stoichiometry is one of my favorite units to teach, and many of my students in the past, and I have been teaching for more than 20 years, have felt that stoichiometry was their favorite unit, and I know that some of you are going to think that too. Now, it sounds a little bit scary, but I can assure you it's not. Stoichiometry is like bookkeeping for chemistry, and it's or we can make an analogy of a recipe. It's like having the right recipe for the reactants to make a certain amount of product. So just to get into the mindset of what to expect, I want you just to look at this question. How many bicycles can be assembled from the parts shown? We have 8 wheels, we have 3 pedal assemblies, and we have 4 frames. So if we look at the wheels by themselves, from 8 wheels, we could potentially get 4 bikes. From 4 frames, we could potentially get 4 bikes. But with the given ingredients that are there, we only have 3 pedal assemblies. So this is what's going to happen. From 3 pedal assemblies, we can construct 3 bikes. So when you take all of this into consideration, we are only going to make 3 bikes. The pedal assemblies are limiting that. So the limiting part of this is the number of pedal assemblies. So all of our pedal assemblies get used up, and we have an extra frame and an extra set of wheels. So a similar analogy can be thought about when we talk about peanut butter and jelly sandwiches. So I have a scenario in which I have a loaf of bread. There are 22 slices. This jar of peanut butter has 32 servings, and this jar of jelly has 48 servings. So looking at each of them individually, let's look at the potential number of sandwiches that each of them could make. So if we don't consider the peanut butter and the jelly, how many sandwiches can be made with this loaf of bread, assuming that we have 2 pieces of bread per sandwich? And the answer is 11. I'm not sure why it's taking so long for me to click through this. If we do not take into consideration the bread or the jelly, the question is how many sandwiches could we make if we have a jar of peanut butter with 32 servings? And the answer is 32 sandwiches. Now, if we do not take into consideration the number of slices of bread or peanut butter, and we have a jar of jelly, how many sandwiches could potentially be made, assuming that 1 serving goes to 1 sandwich? And the answer is 48 sandwiches. So if we take all 3 of them considered, how many sandwiches can be made? And the answer is 11. Which of these ingredients is going to run out first? And you're right, it is the bread. How many servings of peanut butter are going to be left? If we make 11 sandwiches and we start with 32 servings of peanut butter, how many servings will be left? We're going to have 21 servings of peanut butter left. And how many servings of jelly are going to be left in the jar? If we started with 48 servings of jelly and we used up 11 of them, and the answer is 37. So in this situation, our bread is controlling the number of sandwiches that can be made. Now, let's say I had an unlimited amount of bread. Then I could only make 32 sandwiches because my peanut butter would run out first. Or let's say I had unlimited bread and unlimited peanut butter. then I could make 48 servings, because then after that time, my jelly would run out. So just like with this recipe of making a peanut butter and jelly sandwich, we can think of this in terms of chemical equations. I literally am having to choose this, click this like 10 times, maybe more. So how does this relate to chemistry? If we think of this as an equation, 2 slices of bread plus 1 serving of peanut butter plus 1 serving of jelly gives us 1 sandwich. With a given number of ingredients, one of the ingredients is always going to run out first. And it's not always going to be the same one. It's going to depend on the situation. But the one that runs out first is going to limit the number of sandwiches that you make. So if we think of the ingredients as reactants and the sandwich as a product, we have this balanced chemical equation. You have seen this reaction before, where we take magnesium and ignite it, and we produce magnesium oxide. Let's say I'm interested in making some magnesium oxide because I need to use it for an experiment, and I need exactly 5 grams of it. So if I don't want to use any more magnesium than what I need to, I want to figure out exactly how much magnesium am I going to need to make my 5 grams of magnesium oxide. I don't want to use any more than that. That would be wasteful. And a lot of substances are quite expensive. So with reaction stoichiometry, stoichiometry asks these types of questions. If we start with a certain amount of reactant, how much product can we make? So let's say I am running a factory that makes fertilizer, and one of the main ingredients in fertilizer is ammonia. So if I have 10 tons of ammonia, how much fertilizer can we make? Or you could ask this type of question. I want to make a certain amount of product. How many grams of each reactant do I need so that there isn't any left over? If I'm in industry, I don't want to have to purchase and use any more supplies than what's needed, because that's wasteful. So when on an industrial scale, when we are making chemicals as a business, we have to be really, really smart about how much of each thing we need, and we have to be able to predict how much we're going to make. And that all comes down to dollars and cents in reality, knowing those things, because these are money-making ventures. Stoichiometry involves mass relationships between reactants and products. If I start with a certain number of grams, how much product will I make? If I want to make a certain number of grams of product, how many grams will I need? So there are mass relationships. In stoichiometry, a balanced chemical equation is always necessary. We've learned how to balance equations, and this is where we get to put that skill to a test. And in stoichiometry calculations, it's also necessary to calculate the molar mass of a substance. So the good thing about it is, before we really jump into this head first, we are going to take some baby steps. And we're going to practice balancing chemical equations, and we're going to practice calculating molar mass just to kind of ease our way into stoichiometry. I still have to click this a lot. So here's an example of the type of question that we could explore. So this is one of my favorite chemical reactions. If we take a copper wire and put it into some silver nitrate, which is a clear and colorless liquid, silver starts to form on there. And you can see down here the silver is starting to form. And eventually, all of one of the ingredients is going to be used up and the reaction is going to stop. So here's the question. How many grams of silver will we produce if 5 grams of silver nitrate reacts with the copper? So I have 5 grams of silver nitrate, and I want to know how much silver I'm going to produce. Or maybe I want to make 10 grams of silver, and I need to know how much copper is going to be required to make 10 grams of silver. So that leads me to something that I want to mention, because I'm going to talk about this all the time with all of my problems. I am always going to be interested in two substances. Two substances. One substance is the given, which is always associated with a number, and I call it substance A. And we always start with A and we want to end with B. So the next is the substance that we need to find out information about. So this is what the question is asking. It's the substance that the question is asking about, which is B. It doesn't matter if there are 7 different substances in the chemical reaction. We are always only interested in 2 of them. So it's important to identify which substances are which. So we're going to practice with that. This is the same question. How many grams of silver will we produce if 5 grams of silver nitrate reacts with copper? What I do first to find my A is I look for the number and I figure out what it's talking about. 5 grams of silver nitrate. That means silver nitrate is my A. I'm just going to put a little A there. And this problem mentions silver and it also mentions copper, but I need to figure out what is it that I'm trying to find out about. And I look for the question of how many or what mass will be needed. So here it is, how many grams of silver will we produce? So that is my substance B. So I just want to see if I can change color here. So in the next question, it's the same reaction, but I'm asking a different question. And I'm going to have a different A and a different B for every question that gets asked. How much copper is required to produce 10 grams of silver? I look for the number first. I know that that's my A. So in my second problem, my silver is my A. And I want to know how much copper is required, which makes copper my B. So we will practice with identifying A and B before we really jump into stoichiometric calculations. So you are going to get asked, you're going to have an assignment associated in which you answer these questions. And if you are filling out the assignment at the same time as watching this, you could pause this right now and go back, or you may have been following along to what types of questions does stoichiometry ask, what does stoichiometry involve the mass relationships between, and what is always necessary for stoichiometry calculations. And there's another question that I forgot to add to that, which is what extra skill will you need? So another definition, when we have things reacting, we always have something run out first, and that controls how much product we're going to make. The limiting reactant controls the amount of product that forms. It's going to run out first. When it's all gone, the reaction stops. In our peanut butter and jelly sandwich example, it was the bread. In our bicycle example, it was the pedal assemblies. The excess reactant is what gets left over. So after the reaction stops, there might still be some extra reactant that remains unreacted. And we like to plan for this so that there is as little excess reactant as possible. But sometimes We can't control that. We can't really plan for it. So you have to consider that after a reaction is finished, there still might be some of this reactant lingering around because it didn't react. So in the review questions that you're going to have to answer, what are the characteristics of a limiting reactant and what are the characteristics of an excess reactant? The next thing I want to talk about is a mole ratio. A mole ratio is a conversion factor that relates the amounts in moles of any two substances involved in a chemical reaction. So with aluminum oxide, aluminum has a +3 charge, oxide has a -2 charge. The formula for aluminum oxide is Al2O3. The formula for aluminum is just aluminum, and the formula for oxygen is O2. So if we balance this, my coefficients become 2Al2O3, 4 aluminums, and 3 oxygens. Now, in stoichiometry, these big numbers here always become part of the mole ratio. The mole ratio is something that every single stoichiometry problem uses. So here I'm going to first compare Al2, hang on a sec, moles of Al2O3 compared to moles of Al. I can compare moles of Al2O3 to moles of O2. Or I could compare moles of Al to moles of O2. Now, the opposite of these are also true. So another conversion factor could be the reciprocal of this. But the place that we get this number from is our balanced coefficient. So for every 2 moles of aluminum oxide, I have 4 moles of aluminum. For every 2 moles of aluminum oxide, I have 3 moles of oxygen. And for every 4 moles of oxygen, I have 3 moles of O2. So this is the mole conversion, the mole ratio, and these numbers come from the balanced chemical equation. Like that. So here is a reaction for you to practice. What are 3 possible conversion factors for this reaction? And then I would like you to practice this one as well. What numbers would we put into each of these conversion factors? And I will talk about molar mass before we start the next presentation. And this is where I'm going to end this one. So you will answer questions and you will predict mole ratios associated with the questions that were asked in this presentation.